Hello everyone, my name is Razan Ahmed. I'm a master's student at Texas A&M University at Qatar, and I work under the supervision of Dr. Al-Mohannadi and Dr. Patrick Linky. Today I will present our work on sustainable resource integration networks in industrial clusters. Climate change has been a defining issue of our time, mainly global warming, which is one of the largest problems of human-caused climate change. And as economies and population grow, so does the cumulative level of greenhouse gases. Another global concern is the resource depletion, where the overconsumption and increase in demand lead to the scarcity of our natural resources. Multiple global efforts have been directed towards taking action through showcases that provide solutions in annual conferences, and also through preparing annual assessment reports, such as the IPCC report, concluding that without taking action today, adapting to those impacts will be impossible in the future. With the growing of industrialization, the industrial sector has been a huge contributor to the cumulative level of greenhouse gas emissions, whether it's from process emissions or from energy production directly or indirectly. By 2017, carbon emissions increased by 1.7%, and in 2018, it increased further by 2.7%, and that's only from the industrial sector. One proposed solution to reduce the impact of the industrial sector is resource management through creating eco-industrial parks where resources are exchanged within processes through heat and mass integration, and through capturing and treating emissions. Capturing emissions results in less environmental impact. However, it comes with a cost, which decreases the overall profit of the cluster. Therefore, there is always a trade-off between economic and environmental performance. An aspect that takes into account the trade-off is the multi-objective optimization. It answers questions like, what is the optimum case where both emissions are minimized and profit is maximized? So, it simultaneously optimizes more than one objective function, such as economic and environmental performance. Previous work has been done in both the area of resource integration and multi-objective optimization. In resource integration, multiple approaches have been introduced that integrate water, hydrogen, energy, natural gas, CO2 within clusters. However, the integration of networks of these methods integrate 1, 2, or a maximum of 3 resources at a time. A recent approach introduced by our team in the paper, Synthesis of Integrated Processing Clusters, takes into account this gap and introduces a holistic integration model that allows the integration of all possible material and energy resources. In terms of multi-objective optimization, mathematical models have been introduced and applied in the area of process integration. However, the application is mostly limited to energy and work integration. Two of the most prominent multi-objective optimization models are the weighted average methods, where objective functions are identified and each objective function is assigned a weight, and then an overall performance indicator is optimized. Another method is the augmented epsilon constraint method, which is an improvement of the original epsilon constraint method, where the multi-objective optimization problem is converted to a single objective by setting constraints. The two methods result in a Pareto set of solution in which each solution is optimum and represents a trade-off between the objective function. Our proposed method is the multi-objective integration model. in which we use the holistic resource integration model introduced by our team earlier, and we use the multi-objective optimization models to introduce a new approach that allows the simultaneous optimization of more than one objective function of an integration network, where all resources are allowed to be integrated in a cluster. So I will be presenting first the integration model, then the multi-objective optimization models, and then the superstructure that illustrates the whole method. The holistic integration model represents the cluster as follows. We have an industrial cluster, which is associated with resources. The resources can be raw materials, products, wastes, energy resources, and each resource is represented as a line, which has specifications of temperature, pressure, and composition. The resource can enter the cluster as fresh feed or can leave as product or waste. The resource line is also connected to plants, which means that it's either produced or consumed by the plant. And the cluster is composed of multiple plants as well, which can be production plants or waste treatment or capture units. Finally, each resource can be exchanged within the cluster through the infrastructure line that's shown in yellow. The integration model is composed of two things, the objective function and the constraints. The paper presents the objective function as a single objective, which is to maximize the profit, while it's subjected to multiple constraints, such as mass balances and flow limits. The equations here present the economic calculations, balances around the cluster and around the plants, which are all a part of the model. Moving to the multi-objective model formulation and starting with the weighted average method, first, worst and best values for each objective function are specified. And then the values are used to define an overall performance indicator, which is defined by this equation we see here, where VI is the objective function performance indicator, and it's a variable in the model. WI is the worst value, while BI is the best value. Small wi here is the weight assigned for each objective function, which takes me to the next step, which is generating different weight assignments. Different weight assignments are generated in order to generate different optimum solutions. And in order to guarantee fair distribution of the weights and covering a wide range of different distributions, we specify an increment and we create a matrix with all the possible weight assignments for the specified increment, and where all the weights for the objective functions add up to 100%. Finally, for each weight distribution, the overall performance indicator is optimized and the optimum solution is obtained. As I mentioned before, the augmented epsilon constraint converts the multi-objective problem to a single one. First, we obtain a payoff table. The payoff table is a table that shows the extreme values of the Pareto curve. In order to create the payoff table, lexicographic optimization is performed. First, by optimizing the first objective function, and then taking that optimum value and setting it as a constraint to optimize the second objective function, and so on. These values create the first row of the payoff table. And then, in order to create the second row, the same process is repeated, but starting with the second objective function to be optimized. Once we create a payoff table, the extreme values from the table are taken and constraint intervals are generated in order to have more than one possible optimum solution. And then the different constraint values for the different objective functions, other than the main function, are combined and a new table for the runs is generated. The main objective function then is optimized using the constraint table for each objective function. Once optimum values are generated for the weighted average method and the augmented epsilon constraint, Pareto curves are generated. The picture we see here shows the whole optimization approach. On the left side, we start with the integration model, in which inputs for that are process parameters, resource conditions, and cost parameters. And then this model gives us information about the economic, environmental, or it could be social performance of the cluster, and these act as input to the multi-objective optimization model. From the multi-objective optimization model, we get the Pareto optimal set of solutions, which are basically economic or environmental or social performances, and each optimum solution corresponds to a different cluster design. I will illustrate our method now through the multi-objective optimization of a carbon dioxide converting cluster. The cluster we're looking into utilizes CO2, water, and air as the only raw materials. Two products that can be synthesized from CO2 are methanol and urea. So we add production plants for those. Since more raw materials are needed for the production of these products, such as ammonia, hydrogen, and nitrogen, which are all intermediates, an air separation unit, water splitting, and ammonia production are added. These units come with emissions and waste streams as well, and they consume energy. So resource lines for those are added as well. In order to allow emission capture and further CO2 conversion, carbon capture unit and sequestration are added. And also, a unit for water treatment is added as well. The cluster is required to convert 120,000 metric ton of CO2 per year, which enters at no cost, and a tax of $20 per ton is imposed on any CO2 that leaves. The two objective functions of the study are economic and environmental performance. The environmental performance indicator is the CO2 emissions, which comes from the methanol and the urea plants, and also their capture units. For the economic performance, the performance indicator selected for it is the profit, which comes from selling methanol, urea, and ammonia. As explained before, the problem data are the inputs needed for the two models. We have the material process parameters, the energy process parameters, constraints, where here we have a maximum capacity of 100,000 ton per year for the production of the plants. We also have resource conditions, which are specified for each line in terms of temperature, pressure, and composition. We also have the composition of the carbon dioxide in each stream that leaves the cluster. Cost information are also available in terms of capital costs and resource prices. For the weighted average method, an increment of 5% is selected, and the table here shows the weight distribution between the two objectives. And best and worst values for each performance indicator is also specified for the weighted average method. For the augmented epsilon constraint method, a total of 10 constraint intervals are selected within the payoff table. The graph shown here illustrates the result of the multi-objective integration approach using the two methods. We see here that there is a trade-off between the two indicators, since increasing the profit increases the emissions. And as can be seen, the Pareto curve of both methods are identical. Each point in the curve corresponds to a different design, as in different capacity for each plant in the cluster. However, three main designs were obtained. In the first region, highlighted in pink, all production plants are active and excess carbon dioxide is sequestered. In the second region, highlighted in yellow, methanol plant is deactivated and more CO2 is sequestered since less emissions are allowed. And then in the third design in blue, which is at 0 emissions, here urea and methanol plants are both deactivated since all have inefficient carbon capture units and only ammonia is produced. This design still corresponds to some profit since both ammonia and oxygen are being sold. To conclude, in this study, a multi-objective integration model was proposed, which combines an integration model that allows interaction of multiple resources and two multi-objective optimization models, which are the weighted average method and the augmented epsilon constraint. The model allows the integration of all resources in a cluster while simultaneously optimize the economic and the environmental performance. A CO2 converting cluster was optimized using only air, water, and carbon dioxide to produce value-added products, and it was optimized in terms of profit and carbon dioxide emissions. Then Pareto curves were generated that captures the trade-off between the two objective functions, and we concluded that the weighted average method and the augmented epsilon constraint method result in the same Pareto curves. In this case study, we looked into the economic objective function and the environmental objective function. So we optimized two objective functions at a time. Current work that we're exploring is the extension to three objective functions. Therefore, we added the minimization of resource depletion, and in this case, we looked into water consumption as a performance indicator, in which the total water consumption is the summation of all the water that's fed into the cluster. Therefore, what we're trying to accomplish is to generate a Pareto curve that optimizes or that includes Pareto optimal solutions of the three objective functions at a time. This was the end of our presentation, and thank you very much.